The Bob Murphy Show, episode 287.
There's a tidal wave coming. What you gonna do?
Get ready for another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. It's your source for commentary and interviews conducted by a Christian and economist. Now here's your host, Bob Murphy.
Well, everybody, we are going to geek out on this episode. So, to set the stage, back on episode 229, which was published on February 4th, 2022, I had Steve Patterson on. And the title of that episode was, Bob Murphy Admits Steve Patterson Was Right About the Problems with Infinity. And specifically, the springboard for that episode was something that's called Riemann's Rearrangement Theorem. And it had to do with a quirk, certain types of infinite series. When you add up their elements, weird results come out. So I had Steve on to say, Steve, I knew it's been your position for some time now that the way mathematicians introduced the notion of infinity, as a limit, like it's not a number per se, but just the way mathematicians handle the notion of infinity leads to absurdities. That was something Steve had been saying for a long time. And I was dismissing him. Just in general, his critique of math I thought was silly that, oh, come on, Steve, you're out of your element, Donnie, that kind of thing. But then when I encountered this Riemann's Rearrangement Theorem, I was like, okay, yeah, that is crazy. If the way mathematicians deal with these concepts allows this result to stand, they must be doing something wrong. And so then I had Steve back on and we chortled about how much wiser we were than all the mathematicians from Cantor on down. Okay, so believe it or not, I got, I don't want to say the most, put it this way. I cannot remember there being more pushback on an episode than that one. And Steve himself said he gets more pushback when he criticizes math than when he talks about religion. Like, people are more dogmatic about math than they are about whether you're saved spiritually. So for a while, and this was totally my fault, I just kept putting it off, but I wanted to bring somebody on to sort of give the defense of standard orthodox mathematics, and Ian Deters rose to the challenge. So let me read just a bio of Ian, just so you know where he's coming from. And then what I'm going to do is have a long excerpt that I gave at the beginning of episode 229, where I just go through and explain what Riemann's Rearrangement Theorem is. All right, so I'll give you a hint on the timing of that in a second here, so you can skip it if you want. But since that is such a central element, even almost in a sense, even more so for this episode, 287 that you're listening to right now, because Ian is going to basically defend higher mathematics from the charge that there's something fundamentally wrong with it because Riemann's Rearrangement Theorem is nutty. And so any discipline that would allow that must be crazy. That's kind of what Steve and I were saying back in 229. And so Ian's going to come and defend math. All right, so first let me just read Ian's bio, and then, like I say, I'll give you a heads up on how long the tutorial is. Ian Deters holds a PhD in theoretical mathematics and complex and functional analysis, is an associate of the Casualty Actuarial Society, and leads the data science team at MedPro Group, a medical malpractice insurer. His current area of research is the application of theoretical mathematics to provide the foundation for machine learning, the unification of various machine learning methodologies, and a movement toward the creation of models which are simultaneously precise and explicable. He may be contacted through his website at www.iandeters, and that's DETERS.com. So now that I've given that formal introduction, we're going to have an interlude. Is that the word I want? It's basically 40 minutes. It's 39 minutes and change is the portion that I'm excerpting. It's not plagiarism because I'm stealing from myself from the previous episode and recycling it here, so you don't have to go look it up if you don't want to. If you don't want to go look it up, but you want to have it right here is what I'm saying. Just forget me to go through what Riemann's rearrangement theorem is. By the way, just, what am I trying to say? It's really cool in and of itself. So if you like math, and if you don't like math, then skip this episode altogether. Like, you're not going to get anything. It's not like we talk about, I don't know, Rothbard and capital theory and private defense companies or something. No, this episode is all about math. So if you don't like that, that's okay. But this isn't going to be your cup of tea. But if you do like math, make sure you listen for this explanation of Riemann's rearrangement theorem if you haven't heard it before, because it's mind-blowing. Right? And so that is roughly 40 minutes if you want to try to skip ahead, if you don't want to hear it. Ready, go. Okay, so likewise, now I'm saying what I had thought mathematics was free from that, because I thought it was so logical and rigorous that fallacies couldn't creep in there because they would be identified. They would stick out like a sore thumb. And yet, to me, it seems like there's something that, that I would say it's a contradiction. And hence, the mathematicians should have realized, okay, we made a false step here. They don't think that in general. Okay, so with all that prelude, let me go ahead and start giving you what you need to understand Riemann's result. Okay, so first of all, let's talk about a finite series, or a sum, I should say. Okay, so just think of this. 1 plus 2 plus 3 plus 4 plus 5. What does that equal? It equals 15, right? You can do it manually in your head, or you can use the trick. I think Gauss developed this trick when he was like a little kid in school, that you can go to the halfway point, which is 3, and then multiply it by the number of digits, which is 5, right? Because you can like take 2 away from the 5 and move it over to the 1. So it's a 3 on the left and a 3 on the right. And then take 1 away from the 4 and move it over to the 2. So it's a 3 and then a 3, right? So if you want to do 1 plus 2 plus 3 plus 4, all the way up to plus 100, or you can do 101, you do the same trick. You find the mid number, and then that's what they're all going to be on average, and then multiply it by the total number of numbers, and that's how you get the sum really fast. Okay, so there's an anecdote that Gauss, the teacher, gave the kids some busy work, and said, okay, everybody take out your little slates and, and your chalk or whatever, and I don't know if they used chalk or coal, who the heck knows, but they did something back then. They didn't have iPads, that's for sure. Tell me the sum of 1 plus 2 plus 3 plus 100. And so all the kids are sitting there, and the teacher's, whatever, doing some opium or whatever they do. And little Gauss is just looking out the window, thinking about stuff. And then he just writes down the answer on a piece of paper and goes up and hands to the teacher, and he's right. And the teacher's astonished, like, how'd you do that? And he said, well, because I just pictured it in my head. And I realized I could, for each number going left and right, I could just take some from the right one and bring it over so that, it would just be the same number added 100 times. And so then it was just 100 times that, right? And so specifically, just so you're going to, so 1 up to 100, the midpoint is actually, because there's an even number. So there's not one number that's the midpoint. So it's like in between. So what's 1 up through 50 is the first 50, right? And then 51 up to 100 is the second 50. So the midpoint is actually 50.5, right? Because like if you're picturing it in your head, like 1 plus 2 plus 3, all the way, okay? And so then he realized, okay, so on average they're 50.5, and then there's 100 of them. So it's 5,050 is the sum. And so he just did that, just picturing it in his head for a few seconds, and then went up and said 5,050. So if you sit there and manually add them up and did it right and didn't make a mistake, you'd get the same number. But, he did it very elegantly. And apparently, as the anecdote goes, the teacher was like, go back to your desk and do it the right way. Which, who knows whether that actually happened, but that's hilarious if that's what happened. Welcome to the world, Gauss. Okay, so anyway, back to what I was saying. That was sort of just a tangent that wasn't necessary for this episode. So 1 plus 2 plus 3 plus 4 plus 5, you can, do it manually, or you can just say, 3 is the midpoint, and 3 times 5 is 15, right? So that's what it equals. So now I want to say to you, if you agree that 1 plus 2 plus 3 plus 4 plus 5 equals 15, what if I rearranged those numbers? Like, what about 1 plus 3 plus 2 plus 5 plus 4? So it's the same numbers, they're just in a different order. What does that equal? And I think you'd agree it's 15, right? So you can do it manually and check it, but also just the nature of how addition works. What is that? The commutative property. You know that the order shouldn't matter. When you rearrange the order of stuff you're adding together, that doesn't change what the sum is. Okay, so what Riemann generally, again, it's not that he discovered this per se. Other people had discovered instances of it. And then Riemann kind of came up with a general theorem to show the big picture of what was happening. What Riemann discovered was if you have infinite sums, right? So series that go on forever, like sequences of numbers that you're adding together, and under certain conditions, even though in one particular order the numbers add up. Well, let me go ahead and state it. If what you have is an infinite series and it consists of positive and negative numbers, and if you just looked at the positive numbers, it would go to infinity. And if you just looked at the negative numbers, it would go to negative infinity if you added them up. But if you combine them so that they sum to a finite number, for that kind of a series, which is called a conditionally convergent series, you can rearrange its terms and make it add up to any number you want. Okay? So it's not just that by rearranging it, you can come up with a different number. It's that you can tell me ahead of time, what do you want this series to add up to? And I can tell you the number, the target, and I can rearrange the terms in that series such that they add up to that number. Or I can say, rearrange the terms in such a way that they don't add up to a finite number, that the whole thing added together goes to infinity. Okay? And so that would be like saying, in a finite context, that would be like saying 1 plus 2 plus 3 plus 4 plus 5 equals 15. If I then now you tell me, what do you want those to add up to? And then I can rearrange them to add up to that number. Right? So it's not just that if you rearranged it in a certain way, it happens to be a different number. Imagine if I could make that sum be any number you wanted just by rearranging the terms a certain way. So you would realize that would be crazy, right? That no matter how you rearrange those terms, it adds up to 15. So it's one number, let alone an infinite number, meaning that I can make it add up to anything I want. Okay, so again, let me just state it again in words. What Riemann discovered was if you have an infinite series with the following properties, so it consists of positive and negative numbers, and if you just looked at the positive ones and added them together, it wouldn't be finite. It would go to infinity. If you just looked at the negative numbers and added them together, they would go to negative infinity. But when you combine them in the same sequence or series and you add them up that way, they converge to a finite number. All right. And then what the term for that type of a thing is called a conditionally convergent series. For that thing, for anything that has those properties, Riemann said, you tell me what you want that to add up to, and then I will show you how to rearrange the terms in that series, right? So he's not adding in different numbers. He's taking that series as it is and then just rearranging the terms, the order in which you add the terms up. That's all he's doing. He's not putting in new numbers. He's not pulling up. He's not removing numbers from it. He's just taking the existing set of those numbers that happen to be in a particular order originally that added up to some finite number. And then he's saying, what do you want it to add up to? You tell me. You tell him ahead of time. And he says, okay, here's how you would get to that number. And I can rearrange these terms to give, here's the process, the procedure you would use, the algorithm to take that sequence, that infinitely long sequence of numbers and rearrange them in such a way that when you add them up, the way, how do mathematicians add up an infinite string of numbers? Well, there's a way, and we'll talk about that in a minute. When you add them up, it yields that number you just told me. Or if you say, can you rearrange this same sequence of numbers, just change the order in which we add them up, such that when you go to do it, you say, this doesn't converge to a finite number. It just gets bigger and bigger without limit. He said, we could do that too. You tell me, what do you want? All right, so that's what his result is. And I'm claiming, if you let that sink in, what he's saying, to me, that shows there's something crazy going on with the way mathematicians handle infinite series, or adding an infinite series and the definitions they use to say, what does it mean to say this is the sum of an infinite number of numbers, okay? Or a string of numbers that has infinitely many elements. So this dovetails with the kind of stuff Steve Patterson's talking about. That's one of his points, that when mathematicians started incorporating notions of infinity and started doing arithmetical operations on sets that contained an infinite number of elements, as if, it's like finite, it's like doing stuff on a finite number, except we're just going to let it go on forever. And what would it look like if in principle we just did this same procedure forever? and then it yields a result. And Steve is saying something's goofy going on there because it pops out absurdities. And so normally in math, this is me talking now, there's proof, like things called like a proof by contradiction. That if you want to prove something, one way of doing it, like you want to prove X, let's say whatever X is, some statement, some condition. One way of doing it is to say, let's assume not X, and then use the standard rules of logical deduction. And then if we can generate a contradiction, that means not X must not be true, because you shouldn't be able to generate a contradiction in math. And so then you say, okay, because we've just shown if we assume not X, it yields a contradiction, therefore we can conclude X must be true. Because if we assume not X, our heads explode and we don't want that to happen. Okay? And so I'm saying here, likewise, it seems to me mathematicians are admitting, okay, these procedures we use or these definitions for what does it mean to add up an infinite sequence of numbers or infinite series and come up with a sum to say that is what we mean by saying this is the answer for adding up this infinite number of members of this set, allows you to say, oh, for certain types of these animals, when you just rearrange the order of their elements and add them up again, you get a different number. The answer is different. And again, I want to stress here, it's not that it's infinity, right? Because there's weird stuff that goes on. Like you might say, like, let me give you an example. I could say 1 plus 2 plus 3 plus 4 plus 5, forever. What does that equal? Well, it doesn't equal anything. You could say it's boundless. You can loosely speaking say it equals infinity. Technically, that's ungrammatical. You would just say the limit of that is boundless. Okay? Loosely speaking, you could say it equals infinity. Okay. Now, what if I double each one? What if I say, what's 2 plus 4 plus 8 plus 16? Or wait, no, I'm doing that wrong. 2 plus 4 plus 6 plus 8, and so forth, right? I'm not doubling each element, I'm doubling the original thing, right? You could do that. You might want to say, oh, that equals 2 times infinity, right? Because each element is twice as big as the original one. So if the original one adds up to infinity, then the second one should add up to double infinity. But infinity is infinity. What's 2 times infinity? It's just infinity, right? So you might think that that's the kind of semantic trick that we're playing here. Like, oh yeah, Bob, when stuff, you add up infinite stuff, weird things. And that's not what's going on here. So I want to be clear. What I'm saying, what Riemann found is much weirder than that. Because these series do have an infinite number of elements, but it's not that they, quote, add up to infinity. That's not what I'm saying. What I'm saying is you can have a series that the standard way that mathematicians talk about what does it mean to add these numbers up in this particular order, it comes up with a finite number. It comes up with a 0 or logarithm of 2 or whatever. And then they say, okay, so it's not infinite, it's not infinity. The things add up to a finite number. And then they're just saying you rearrange the order of those elements and add them up again using the same definition that mathematicians use for what does it mean to add up a list of infinite numbers or an infinitely long list. And there's a different answer that's also finite. Okay, so that's weird. And I'll leave it at that in terms of the stating what it is. Okay, now let me just give you a little bit more. We'll just go for a few more minutes here just to warm you up so you can kind of see a little bit more concretely how this stuff works. Okay, so what about if I just start adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 forever? Clearly, you would say that diverges. That's what the language they would use. Loosely speaking, you could say it equals infinity, but again, that's not really grammatical. You'd say it tends toward infinity, or you could say any finite number you pick, no matter how big, I can continue that sum. I can continue that series out, and eventually I will be bigger than that number. So you could say, well, what about 60 quadrillion? If I continue that 1 plus 2 plus 3 plus 4 long enough, and I could figure it out for you if you wanted, at some point I would have, even with just the partial sum, not taking the whole series, but just some of it, I would have exceeded 60 quadrillion, or whatever number I said. And I could do that for any finite number you pick. I can always just keep going on that plus n plus 1 plus n plus 2, and eventually I will surpass that number, that ceiling that you picked. So that's why you would say that series diverges, right? It does not converge to a finite sum. Okay. What about 1 plus 1 plus 1 plus 1 plus 1 forever? Similar thing, right? So there, So notice in the first one, each element gets arbitrarily big. So let alone, adding up that plus all the previous elements. But even if the elements themselves just are finite numbers, well, even if they stay below some threshold, so like 1 plus 1 plus 1 plus 1 plus 1 never gets bigger than 1, but you can see adding that up forever, it diverges also. Okay? And now, try a different one. What about this? 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus forever, right? So each time I take 1 over, and then it keeps doubling the denominator. That adds up to 1, the way mathematicians define these concepts. Okay, so strictly speaking, you'd say the limit of that series as n goes to infinity is 1. And that's what it means, loosely speaking, to say 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 forever equals 1. And it's really easy for that one. The reason mathematicians use that a lot to get these concepts across is because it's really easy to picture it geometrically. Just imagine a square in your mind. And then at first, and you're moving from left to right. So at first you shade in the left half of the square. And that's 1/2. You've just filled in 1/2 of the area of that square. Now you get your picture in a square where the left half is shaded and the right half is still like open. And now, so that was the adding the 1/2. Now you're going to add the 1/4. And so that's half of the remaining area, right? Because it's 1/2 of 1/2 is 1/4. So of that remaining empty space on the right half of the original square that you just filled in half, again, now cut that in half and fill in the left half of that part. And so now you've just got the rightmost 1/4 is still open and the left 3/4 is now shaded in. And now you're going to color in 1/8. And that's, again, half of what's remaining. So if you're thinking of it that way, you keep doing strips that are always 1/2 of the remaining area of this square that's still needing to be shaded in or colored in. And you could just keep doing that forever. With each step, you just keep filling in 1/2 of the remaining empty space. And so you can see how if you did that forever, what does that mean? If you did the infinite number of steps, eventually, so you got to be precise here. It's not that you would ever actually fill in the full square because you would never complete the process, but you can make the remaining empty space arbitrarily small. And you'd say the limit as n goes to infinity of doing those steps, one at a time discretely, is that the total sum of how much of that square had you colored in would equal 1 or 100% of the square. Or you could look at it the other way and say at any given time or any position in that sequence, how much of the square remains unshaded, and that thing would shrink to 0 eventually. That would be the limit, to be more precise. Okay, so there you can understand the sense in which, if you pictured that, the sense in which mathematicians think that 1/2 plus 1/4 plus 1/8 plus 1/16 plus blah, 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 it converges to 1. That's the precise statement. And then loosely speaking, you say it adds up to 1. That's what they mean. Okay? Now, let me throw another curveball at you. You might think, oh, okay. So what happened there was each extra term that we added on, right? So first it was 1/2, then it was 1/4, then it was 1/8. Notice that those things get really small and they go to 0, right? The bigger it gets, it gets to be 1 over 1,024, 1 over 2,056, that thing gets really, really small. And so it kind of makes sense that as you keep adding constantly shrinking things to the number, the total, the sum of all those things added up, sort of converges to a finite number. Like there's a ceiling above which it can never rise. And that's what it means to say it converges to a finite number. So that's a necessary but an insufficient condition for the thing to if it's all positive numbers, to converge. Okay, so and what I mean by that is you can come up with examples where the numbers you keep adding do shrink to 0, but still the sum itself has no bound. And the most famous one is what's called a harmonic series. So that's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 forever. That thing, even though the individual terms get arbitrarily small, right? Eventually it's like you're doing plus 1 over 17 trillion, which is a very small number. even though each little thing that you add to it gets microscopically small, nonetheless, that whole sum diverges. Okay, and I'm not going to prove it. There's a lot of elegant proofs. You want to look this stuff up. I'll obviously put some links, folks, at bobmurphyshow.com/229 for some of this pure math stuff on Wikipedia and other places if you want to see it spelled out more formally. But what it means to say it diverges is you give me any number you want, no matter how big, 60 quadrillion, and I can show you if you just keep doing plus 1/6, plus 1/7, plus 1/8, plus 1/9, at some point, that sum will be bigger than the 60 quadrillion or whatever number I said. Even though you might think that, no, that doesn't sound right because they're shrinking. Well, you've still got an infinite number to add. And, loosely speaking, intuitively, if you want to say, well, the reason those are different is because when it kept getting cut in half, it was like shrinking faster than when you're just, making it go down by n as opposed to 2 to the n in the denominator of each term, right? So the plus 1/4, plus 1/8, plus 1/16, those shrink faster than the plus 1/2, plus 1/3, plus 1/4, if you think about it. And so, if that's the intuition you need to kind of help make that make sense to you, fair enough. Okay. But again, whether it makes sense to you or not, the way mathematicians use these results or define these concepts is that 1/2 plus 1/4 plus 1/8 plus 1/16, that adds up to 1. Whereas 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, blah, 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 forever, that doesn't add up to any finite number. That gets arbitrarily large. And so that you can say that diverges. Okay, so now we got some of those concepts under our belt. And this is all standard stuff you would learn in a, calc sequence. Okay, so now that you got that, again, let me restate now what Riemann's rearrangement theorem found. So if you have a series that consists of positive and negative numbers, and if you just looked at the positive numbers, they would diverge. There would be no upper bound on it. You would add them up and they could always exceed any finite number. And then you also had negative numbers that if you added them up, they would diverge the other way, that there's no lower bound. You could pick negative quadrillion, 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 and yet you keep adding more terms of the negative ones of this original series. Eventually, it's going to be smaller than that. But when you add them together, when you combine those two different things into a particular sequence, if that added up converges, well, the label for that is called, it's a conditionally convergent series. And what Riemann found was, or proved, is that for such a series, you tell me what number you want it to add up to, and I can take that existing series and just rearrange its terms and make it add up to that number. Or if you want, you can say, I want it to diverge, the originals, the series itself, not just the positive and negative components, but the whole thing we added together, positive and negative mixed up, or, put into together with each other. I want them, the way mathematicians add up an infinitely long series, to not have an upper bound. I want to go to positive infinity. You can do that too. All right, and that's what he found. So let me now just give you a particular example just to make sure you understand how this stuff works. Okay, so consider this infinite series. 1 minus 1 plus 1/2 minus 1/2 plus 1/3 minus 1/3 plus 1/4 minus 1/4 forever. Okay, so again, I'll say you start with positive 1, then minus 1. Positive 1/2 minus 1/2. Positive 1/3 minus 1/3. You see, you just keep doing that forever. So that series, the limit of that, as you do the partial sum, you take any finite number of elements in that series and add them up, and it'll yield some number, and then you take the limit of that as n goes to infinity. That sums to 0. Okay, and so notice, because every other term, the thing sums to 0. And then if you think about it, like the amount that it exceeds it one way or the other gets smaller and smaller, right? So you just do the first term, it's 1. Then you add the second term, which is minus 1. Now the partial sum goes to 0, right? Because it's 1 minus 1 is 0. But then if you do the third one, it's 1/2. So now it bumps up again. But then if you do the fourth one, include that, now it's minus 1/2, so it's back down to 0. So notice you keep doing that. The partial sums go like 1, 0, 1/2, 0, 1/4, 0. Or sorry, 1/3, 0, 1/4, 0, 1/5, 0, as you keep adding more and more terms. And so you'll notice that partial sum gets smaller and smaller. Well, it's alternating. It's either 0 or the other thing. And so the limit of that goes to 0. And so that's the sense in which that original series converges to 0. Okay, but notice it's conditionally convergent, right? So if you just looked at the positive elements of that, it's 1 plus 1/2 plus 1/3 plus 1/4, right? And we already argued, I didn't prove it to you, but I'm telling you that's a harmonic series, and that diverges positively, goes to positive infinity. And then likewise, that thing with just negative numbers in front of it diverges to negative infinity. Okay, but yet if you arrange them in that particular order, like I said, where you go 1 minus 1 plus 1/2 minus 1/2 plus 1/3 minus 1/3, it's pretty intuitive to see that thing, quote, adds up to 0. Okay? So now here's what's weird. Up till now, things might have been fine for you. You might have said, okay, yeah, that thing adds up to 0 and I can see how that works. Sure. But now you probably would have thought if that thing adds up to 0, if I rearrange the terms, it should still add up to 0. And yet that's not the case. So here's a particular way to rearrange it. We're going to take that original list of numbers and there's going to be the same numbers constituting this new list. It's just we're going to change the order of them. So specifically what we're going to do is we're going to take 2 positive numbers at a time and then 1 negative one. Okay, so we're going to take that original list and just pull out the first 2 positive numbers, then pull out a negative number, then pull out the next 2 positive numbers, then pull out a negative number, and so on, and add that thing up. And notice it's the same set of numbers, constituents, elements. It's just the order is different. And you say, well, how do you know it's the same number? Because every number in that second set that I construct came from the original one. Like you can, there's a 1-to-1 correspondence. That's like a more formal way of saying it. So every number that was in the original list, we know is going to end up in the new list. And every number in the new list, we know had a corresponding member in the first list. So it's the same set of numbers defined by its elements. It's just the order in which we're adding them is different. Okay, and so specifically, in case you're getting lost, this is what the new sequence looks like, or series looks like. It's 1 plus 1/2 minus 1, plus 1/3 plus 1/4 minus 1/2, plus 1/5 plus 1/6 minus 1/3, and so on forever. So again, that's the same set of numbers in the first list. It's just we're changing the order. Instead of going 1 minus 1 plus 1/2 minus 1/2 plus 1, we're just taking the first 2 positives. So that's why it's 1 plus 1/2, then the first negative, which is -1, then the next 2 positive, which is plus 1/3 plus 1/4, then the next negative, which is -1/2, and so on, right? So it's the same, again, every number that's in that new list or series that I'm listing was in the first one. And going the other way, every number in that first list is in that second one. And notice there's no duplication. It's a 1-to-1 correspondence. Okay. So now, if I just, without context, told you and you had been trained in math to say, hey, the series 1 plus 1/2 minus 1 plus 1/3 plus 1/4 minus 1/2 plus which is that second one we constructed. What is that? You'd say, well, if you just looked at the positive numbers, it diverges to positive infinity. If you just look at the negative elements, it diverges to negative infinity. But if you add them up all together in the particular sequence or order that you just listed them in, it actually conditionally converges to the natural log of 2, which you write out as ln2. Okay, so obviously me just talking to you guys, I'm not going to totally be able to show you that, but that's what it converges to. The natural log of 2, which is not the same thing as 0. The 0 and the natural logarithm of 2 are different numbers. Okay, so that's just one example where we're saying, and so what Riemann showed is this isn't just a rare thing for any conditionally convergent series. You tell me what number you want it to add up to, and I'll show you a way that you can rearrange the elements to add up to that number. All right. And again, that would be like, in a finite context, that would be like saying 1 plus 2 plus 3 plus 4 plus 5 equals 15. But 2 plus 3 plus 1 plus 5 plus 4 equals 7. And that would be crazy. And yet, that's what happens with conditional and convergent series. Okay, so I will stop there. That's enough of a math primer. And thus ends my recapitulation of Riemann's rearrangement theorem. And so we now proceed to my conversation with Ian Deters, who will defend mathematics from the aspersions cast upon it by Steve Patterson and myself. Ian, welcome to the Bob Murphy Show.
Good day, Dr. Murphy. Thanks for having me.
So it's been a while since I had Steve Patterson on to talk about infinities, but at the time, there was a larger than finite amount of outrage at it. Lots of people were mad. Like, it was funny. It was like people were mad. And I told Steve that and he even alluded to that in his discussion, that he said people get more mad about that than about religion even, or politics even. So
right.
Anyway, so that's and Ian, I don't know if I did. So what I will have done, the listener, that whole beginning part of the episode with Steve, where I go through and explain what Riemann's rearrangement theorem is, I will have included that here for people who want it, so they already have that in their back pocket.
Yep.
So I know you had come up with an extensive outline of what we're going to go through here.
Yeah.
And so let me bring that up on my end. I suppose maybe just can you briefly, I would have already in the introduction too, given some of your background, but can you maybe just tell a little bit like biographical or autobiographical?
Yeah, sure.
Just about where you're coming from so people know. And like like, are you interested in libertarianism and Austrian economics?
Yeah. Well, after the interview with Patterson, I got a call from Klaus Schwab, and he said that, they're coming after the academy now. Not even mathematics is trustworthy. Ian, go do something about it. And so that's why I wrote you the email. So yeah, it was an interesting thing because you had casually mentioned to me, "Oh, I'm doing an episode on something mathematical. Why don't you listen to it? Tell me what you think." Okay, sure.
Mm-hmm.
So I sat down, and like most, I assume it's the same for you. Most podcasts, I listen to them while I'm doing other things, and I actually literally couldn't. I mean, I suppose I literally could, but I had to keep stopping and taking notes because, as Patterson suggested, there was outrage, but I try not to be merely outraged. I try to do something constructive about it, which is why I wrote you that dissertation of an email in response to try to explain some of the finer points. But my background is in mathematics, so I have a PhD in theoretical math. I am an associate of the Casualty Actuarial Society. I work as the lead data scientist at a medical malpractice insurer. And the things in which I'm interested in terms of research is the construction of mathematical models, in particular statistical models, which are simultaneously explicable and precise. And so those are the things in which I'm interested. And with respect to Austrian economics and libertarianism, absolutely love that stuff. I've got, gone through Human Action, gone through Man, Economy, and State, love Thomas Sowell, Anarchist for Life, all that good stuff. Yeah.
Okay, well, great. So it's interesting because, there's a sort of stereotype that people are attracted to Austrian economics as they're not good at math. So,
yeah, I in going back over some of the material for this, I recalled some of the things that you said in times past, though, that you actually compare the output of Austrian economics to things like geometry, where you say, these things are true; they're deduced from first principles. And so I think that there's more crossover than perhaps is say on the surface. But I am sympathetic in a certain sense to the tone of the show with you and Patterson because of the fact I know it's sort of like in Jurassic Park when he says, "What evolution is the most incredible thing known to man," but you wielded like a child who saw his father's gun. I've seen that attitude with statistical models and whatnot, so I understand that. But I am convinced that with sufficient conversation. There's a great deal of application of mathematics and statistical models in the framework of Austrian economics.
Yeah, and obviously I was being a bit tongue-in-cheek there. And,
Sure.
I think Rothbard was, I don't know if he's a major in statistics, but he was taking a lot of statistics courses. And Mises certainly, he's arguing with his brother on the, underlying foundations of probability theory and stuff. So it's...
Right.
Okay, so why don't we dive right in? I know there's a lot of material here.
Sure.
So do you have that outline in front of you as well, or do you want me just to be...
Oh, yeah, I got it right here.
Okay. So you want to start and say right off the bat that, so I guess why don't we, the three main areas, like the way you sort of parse the episode, is you said number one, mathematics is full of nonsense. 2, the academy is corrupt. And 3, models versus reality. So for folks at home, just giving them the big picture of what we're going to do. So right now we're in the section called mathematics is full of nonsense.
Nonsense.
So, yes. And so, so go ahead. Why don't you take us through your pace, and I'll stop you for clarification, or if I want to perhaps occasionally even disagree.
No, disagree all you like. Let's give the people what they pay for. But anyway, so on the mathematics is full of nonsense part, again, of the episode with you and Patterson. Now, you had come across, apparently recently, the Riemanns Rearrangement Theorem. And that was something that, I got the impression that you were just like, what is this nonsense? What's going on here? This should not be the case. And that sort of roused your suspicions and made you think that, maybe Patterson is right, that, mathematics is shot through with nonsense. And so you have things like Zeno's paradox, but unfortunately calculus solves that. I think it was Patterson who mentioned the magic ellipses or something like that. So when mathematicians are writing formulae or doing proofs, and you got the ... and there's a lot going on in that ... and they're slurring over the details and whatnot. And I have to admit that there can be a certain amount of that, but again, that's a function of the mathematician with whom you're interacting. Serious mathematicians will try to, attend to those things. So anyway, well, why don't we, since the title of that episode was, I think it's, do infinite sets spell the downfall of higher mathematics? Let's start with infinite sets. Does that work?
Yeah, it does. And let me just, again, even though I would have replayed a lot of excerpts from the thing, I don't remember if it, like my particular concern. Let me just state it very succinctly.
Sure.
It's pretty analogous to my thoughts about like economics or other sorts of fields too, where the beginnings are fine,
right?
But it's only later when it gets real advanced that the weirdness and craziness creeps in. And so it's likewise with mathematics. Obviously, I'm not against arithmetic. I'm not even against calculus and those things. But what made me sit up and take notice with the Riemann's rearrangement theorem was I thought it's the way mathematicians handle infinite sums.
Yeah.
It seemed to me that, fine, I get it. Like it's obviously not going to be the same thing as a finite sum. Like they got to come up with procedures and whatnot. But I thought if Riemann's result pops out of that process, that means you did something wrong. That there must have been some absurdity that was introduced earlier on.
Sure.
That's kind of my take. So it's not like saying, oh, math is wrong.
Right.
I'm just saying that area and like what they were assuming, like, well, when it comes to an infinite sum, how about we proceed this way? And that's what we mean when we talk about adding up an infinite, because obviously you add up an infinite number of numbers that, don't shrink, don't converge down that all the answer is infinite or something. But anyway, so, or in one sense, if it would take an infinite long enough time, you say, well, we don't know. We can't add that up because there's an infinite number of elements. Right. Like that would be like a sort of simplistic, literal response. So I'm saying whatever it is that mathematicians say, this is what we mean when we have a ...
Right.
That something's screwy if Riemann's result pops out.
Right.
So that's my position.
Sure. Yeah. So then let's talk about infinite sets and we'll work our way toward the Riemann's rearrangement theorem and the explanation of it on how it fits into a broader context. And I think we'll be in good shape. But I will say this is precisely the case where we have to attend to details. So 2 quotes from Patterson in past episode. He states he thinks a lot of the formal theory around math is imprecise and unnecessary. And then about 9 minutes later, he says he's not interested in the details of mathematics. And while again, I'm sympathetic toward that view because I recognize that a lot of people view mathematics as being quite complex. I assure you, it's no more complex than it needs to be to solve the problems that we're trying to solve. We're not being needlessly complex for the sake of weed out courses or something like that. It's simply the result of trying to solve certain problems. And so, before one more thing before going to infinite sets, I just want to make this point too. There are two sort of statements that were made also during there, which was there's mentioned a few times as the idea of a completed infinity. I literally don't know what that is. I've never heard a mathematician use that phrase. So I think that phrase might be a bit of a red herring. And then the phrase, imagine a circle whose radius is infinite. Again, never something a mathematician that I've ever known has ever said. So let's not get thrown off by that. Okay. So I suppose I should also give my mathematical background for some of the things I'm going to say, which is that I am not a very granular, detailed logician of the type of, say, Russell and Whitehead, guys who are really trying to derive some sort of philosophical foundation for mathematics. That's not my background. I'm sort of maybe a level above that. My background is in what's known as analysis, which you can think of functionally as the basis or the foundation of calculus. Nor am I a historian of mathematics. I've taken a course in it. I read a few books. E.T. Bell, Meta Mathematics, great book. But I'm not going to pretend that I've studied the works of Euler and things like that. Papers from 300 years ago or something. So I'm going to be approaching this from the standpoint of simply trying to provide more context around results pertaining to infinity, and in particular Riemann's rearrangement theorem. That's going to be my tack, and then feel free to poke at whatever you want as we go along. Okay. And so starting there then, my first statement is simply that I don't know about you, but I think I can guess that I cannot think about numbers without thinking about infinite sets. And my guess is that neither can you, and neither can Patterson, and neither can anybody. And the reason for that is quite simple, which is that you can always imagine adding 1 to the maximum number in the set. And because you can always imagine doing that, the idea of an infinite set it's in a certain sense, it's axiomatic to mathematics. And in fact, it is one of the Franco-Zermelo axioms, is the existence of an infinite set. And we typically call that set the natural numbers. Those would be your counting numbers, 1, 2, 3, 4, 5, and so on. There's your ... Mm-hmm. And that's that. And then
well, can I stop you though?
Sure.
So yeah. I understand. Trust me, with all this stuff, I certainly so far understand everything you're saying, where you're coming from.
Yeah.
And probably by the time we're done, I'm going to say, okay, great. Now I've given the listeners the other side. Like, this is the orthodox mathematical response to some of the issues raised.
Yeah.
But I imagine what somebody like Steve would say right there is, what do you mean, Ian? Or maybe he would call you Dr. Deters. That when you say we can't help but think of infinite sets. No, it's the other way around. We can only think of finite sets, and you're saying you can always add 1.
Right.
Okay. And then it's still finite.
Sure.
You literally cannot picture an infinite, you know what I mean? Like it's an idea. You can say the words.
Yeah.
But so I think that's what he would say.
Right. Okay. That's fine. Well, in that case, then in practical terms, I probably can really only imagine sets of, say, 7 elements, because you have to think in practical terms. Is there really a difference between infinity and 5 trillion? In either case, you're not going to write down 5 trillion numbers, nor any more than you can write down,
or like hold them separately in your consciousness. Yeah.
Right. Yeah. And very, very much off to the side, in sort of a related matter, though, David Berlinski makes this point when he's talking about evolution going through all of the different combinatorial explosion that it takes to get all of the gene sequences to actually have species come forth. The probability at some point becomes so astronomical that you just call it 0 and move on with your life. And so it's the same thing here, is that you and I in our daily work, we go about our business doing arithmetic, and we do it with this imaginary set in mind. But all of these things exist within our minds. These are simply ideas that exist within our minds. And so, I mean, I suppose a rejoinder to that would be something like, well, what does it mean for the natural numbers to exist anyway? What does it mean for any idea to exist? The fact of the matter is that ideas exist in our mind, and then we act on those. And of course, the idea of praxeology is a very big idea in Austrian economics, is that because I have the idea of an infinite set, I imagine certain things. Those things manifest themselves through me in the manner in which I, for instance, program computers, which admittedly, and we'll get to this later, which admittedly do a finite number of computations, but the computations they are performing are an approximation to something I imagined in my mind because I have this idea of an infinite set.
Okay.
Does that make sense?
Yes.
Okay. So that's that. And then so once you have that, once you're willing to go along with the idea of an infinite set of natural numbers, then you pretty much you've given the game away.
So in other words, for the folks at home, you're saying really where it's going to come down like this philosophical divide is, does it make sense to think of 1, 2, 3, 4, ... forever?
Yes.
Or not?
Or not. Yeah.
And Steve, I think everyone can understand where Steve's coming from and say, no matter how far you push that,
yeah,
it's always a finite number. But then I think people understand, Ian, where you're coming from, and to say, okay, but like once that procedure is down, like we can certainly think of, like also you can't really think of 1 through 5 trillion, like you said, like
right.
You really actually can't do that. And yet it would be weird to say, come on, the idea of 5 trillion, that's kind of nonsense. Let's not use that anymore.
Right.
Like, for one thing, what would happen with the national debt, right? You wouldn't be able to keep track of it. So
I actually did think about that when I was writing this up, because I just selected a large number like 5 trillion. I'm like, oh, but national debt does exceed that. Yeah, the national debt doesn't exist. What is money, man? So anyway, yeah, okay. And so the reason why I say it comes down to the natural numbers is once you have the natural numbers, then when you try to extend the numbers such that you introduce the idea of zero, it's like, okay, you have this symbol that represents the absence of something. That's a slightly greater deal of sophistication, I think, than the natural numbers. Then you introduce the idea of negative numbers. Now you can, for any positive integer, you can find its pair such that when they add, they cancel and give you zero. Of course, you need that for the idea of debts, right?
Let me slow down. So, Ian, you're saying the progression, whether this happened historically, but certainly like logically, if you're trying to just build from basic, everyone gets how, quantity, like you could teach some Martian or something, our word for 1, for 2, for 3, like they would probably get the abstraction. They wouldn't think we meant 3 screwdrivers, that we were saying
right.
Quantity. If we were like, holding up things and going 1, 2, 3, like we're teaching the Martian how to speak English.
Right.
It would be hard to show them what 0 means. And it would be really hard to show them -3. And so the way that comes about is you can do addition, like, 3 and 4 is 7. And that's easy, to enumerate and to like talk about that process of addition. And then you're saying, okay, and then once you have 0 is a separate thing now. Okay, so what we mean by a negative number is, 7 plus -7 is 0.
Right.
Like that's, okay.
Yeah, exactly. And of course, that comes in very naturally through the idea of banking and whatnot. The algebraic way of thinking about it is trying to solve progressively more complex equations. So for instance, without the number 0, you can't solve the equation 1 plus x equals 1. But if you're willing to include it, if you're willing to extend the natural numbers in a very obvious way, then you can. Integers, like, I said, they come from whole numbers. They allow you, for instance, to solve the equation 1 plus x equals 0. So now that you've got 0, you can ask yourself, well, what do I add to a natural number to get 0? And so that's another way of thinking about it. Of course, that's a more abstract way of thinking about it. The algebraists, that's typically how they think about it, is they say, okay, I want to solve this set of equations. Do I have sufficient, are my numbers sufficiently rich so that I can solve this equation? Yes or no?
Okay, yeah. Okay, so let me just make sure. So you're saying if, you could imagine, you could introduce algebra, and if you just did it on the natural numbers, that would work for a lot of problems. 3 plus x equals 7. What's x? You could solve that. Oh, x equals 4.
Right.
You could subtract the 3 from both sides, that kind of stuff. But then the problem would be is if all you had is your set of potential things to plug into X was 1, 2, 3, 4, namely the natural numbers.
Right.
Then if you wrote something like 1 plus X equals 1, then you say, how do you say? Oh, just subtract 1 from over, and then you would be able to subtract. But anyway, you would get X equals 0. And so if you didn't know what 0 was at that point, you would be stuck, and you would say this equation has no answer. And so that's how we could formally introduce what do we mean by 0.
Exactly.
And you could say it's the solution to this kind of a problem.
Right. And so you'll find that in mathematics that there are typical ways of imagining sort of the meaning of it external to mathematics itself. Again, such as absence or debt or something like that. And then there's also a formal way to proceed to enlarge these sets of numbers in some reasonable fashion.
The reason I thought it was good to walk through, even though I'm sure everyone at home was like, we got that, but is when it comes to I, then it's not so intuitive. And so that's why I wanted to just drive home something simple.
Yeah, that's correct. And so I'll walk through that when we get to that point. And then rational numbers, of course, come from integers and rational ratio. You're taking the ratio of them. And that's, of course, because sometimes you want to cut things into pieces and you need to keep track of that. And so, again, fractions are very, very, I think, easy to understand in terms of the physical problem you're trying to solve, that of dividing something into pieces.
Okay, just again, make sure. So, folks, what he's doing is he's enlarging the set of numbers. And so we start with the natural, then he showed what the integers were. So that's any negative, like -3, -17, -2 billion, 0, and positives as a set of integers. And then the set of rationals is any number that can be expressed as the ratio of 2 integers.
Right. Yeah.
So
exactly.
like 3/5 or negative, 17/18. Okay.
Yep. Yeah, exactly. Right. And again, the algebraic way of thinking about it is, okay, well, how do you solve the equation 2x plus 3 equals 0? You need to have some sort of number to represent that. And that's, for instance, how you might do it formally. Now, if you take a course in abstract algebra, which reminds me, I wanted to ask you, I should have done that at the beginning, but what is your background in mathematics? How high up did you get? I know your brother has a master's in it.
Well, I didn't get a master, but then we had to know a lot of math to get the PhD in economics at NYU.
Okay.
So I did a lot of set theory and stuff there, but I'm not sure. I think I cobbled a lot of it together just by going and getting books. So I don't even know what label to put on it.
Sure. Okay. No, that's fine.
But I know it's like I got into stuff like, countable infinities and stuff like that, or countable sets versus uncountable, that kind of stuff.
Yep. Okay. Gotcha. And so the process of getting the rationals from the integers, just to be formal here, that's what's known as constructing a field of quotients from an integral domain. And so that's a very general construction that you can do with things that algebraists would study, called integral domains, which are sort of the abstract version of the integers. And then the field of quotients that you construct from an integral domain is sort of the equivalent of what the rationals would be. And so we've got the rationals now. So how do you go from the rationals to the real line? And again, that's a very canonical construction. But this construction, instead of being algebraic in nature, is analytic in nature, in the sense that you're making use of the fact that the rational numbers are what's known as a metric space. And so there is a way to calculate a distance between things. And so there's what's known as completing a metric space. And what that does is it basically says that when you complete a metric space, all what are known as Cauchy sequences converge. And so what a Cauchy sequence is it's a sequence of elements such that the elements in the sequence get closer and closer and closer and closer and closer together over time. And so you can think very, very easily of, say, a decimal expansion, right? If you have a decimal expansion, if you look at the truncations, each successive truncation is within 1 over 10 to some power of the previous term.
Okay.
Yes. Okay. And so the truncations of a decimal expansion are getting ever closer together. The question is, do they converge to something? does that sequence converge to something? And the answer in the case of the rationals is not always. And the obvious the very first thing that you would learn where that doesn't work is, say, the square root of 2. Square root of 2 is an irrational number. The fact that it's irrational comes from a very simple proof by contradiction. And it's one of those proofs that you would do in an undergraduate, like a sophomore level class. Like, here's what proofs are, here's your first homework, kids. And then you go home and you prove that square root of 2 is irrational using argument by contradiction. It's a very classical exercise. And of course, the geometric realization of the square root of 2 comes from, if I hand you a unit square.
Well, can we hang out? I think maybe people are getting a little bit lost. So
sure,
I'm sure they were with you. Okay, there's the natural, the integers,
rationals.
the rationals, and then is the next thing like now, or is it you say, okay, now picture like the real, so picture the real number line.
Yeah, so now we're going to the real number line. Yep.
Like picture between 0 and 1 on a number line, and then like halfway between it, that's 0.5 or 0.5000, and so that's fine. But then there's other ones in there where it doesn't, or like 1/3 is 0.33333, and that's fine. And you can see how okay, but something there are numbers in there that are irrational that cannot be. And by the way, the 0.333 can be expressed as 1 divided by 3.
Right.
So that's a way to see that's rational.
Right. Well,
but now there's numbers in between 0 and 1 that are not rational numbers. That it's there. Like, what do you mean it's there? Well,
exactly. What do you mean that it's there? Yeah. Exactly, precisely.
We can define it, and maybe you want to talk about that more in a second. But
yeah,
I get the idea that okay, if every point in between 0 and 1 represents or corresponds to some number, but they clearly are not all rational, and even though there's a bunch of rational in there, so among other things, irrational cannot be expressed as the ratio of 2 integers. And then now you're telling us the square root of 2 is probably like the most intuitive example of an irrational number.
Yeah, it's the most intuitive example of an irrational number, because if I hand you a unit square, a square whose sides are unit length, what does the Pythagorean theorem say? It says that the length of the hypotenuse is satisfies that length squared equals 1 plus 1. And so it's the number whose square is equal to 2. Okay, fine. Well, you don't have a number. You can't express that if you simply have the rationals. You need to enlarge your set, and the way you enlarge it is you again, in metric spaces, it's what's called completing a metric space. And it basically allows you to put in points for sequences which don't converge, but whose terms get closer and closer. And so you could imagine the decimal expansion of, say, square root of 2 or something like that. Again, if you look at successive truncations, they're within powers of 10 of each other, or 1 over powers of 10 of each other. And so the terms in the sequence are getting closer and closer, but it doesn't go anywhere. It doesn't converge to anything because the square root of 2 it's irrational. And so basically the completion is the filling in of all of those gaps. This is geometrically how you can think of it. If you just have the rationals, what you can think of is you have this line, but it's very porous. It's very porous. It's like a sponge. Right. And then the completion fills in all of those points. And again, that construction is a very canonical construction. It's a very general construction, but that's how you move from the rationals to the reals. It's an analytic construction as opposed to an algebraic one.
Okay, but in terms of the algebraic one, like you're saying, if you did it as you wrote x squared equals 2, and then said solve for that, and you can only use rationals, you'd say, oh wait, I can't then.
You can't. Yeah, you can't solve the equation.
You need to have a bigger set of numbers to plug in to that to be able to solve that algebraic formula, and that's what you said. And they call them irrationals.
Exactly. And so to get just the square root of 2, you can do that using an algebraic move. It's called it's in the topic of extension fields. Is the idea, and there's a very canonical way to basically say, if you have a polynomial with coefficients that are rational, and you need all the solutions of it, you can canonically construct a larger set of numbers to include those solutions. Pardon me. But then there are other numbers that we think of as real numbers, like say pi, which are not the solution to any polynomial equation with rational coefficients. And yet, something like pi is very easy to, again, represent, because you just draw a circle with radius 1, and then you say, what's the area? And if you don't have the real numbers, you don't have a way to represent it. Even if you have all of the solutions to all of the polynomial equations with rational coefficients, you still can't represent pi, and that's because pi is what's known as a transcendental number. The demonstration of that is actually quite complex. It took a while to get the square root of 2 irrational is like no problem. It's like sophomore level. It's like, how hard can pi be? Very difficult. The proof that
so there's a sense in which pi is more elusive than the square root of 2, even though they're both irrational?
Yes, because and pi and e are both what are known as transcendental. So they don't have an obvious algebraic expression the same way the cubed root of 17 does. You can imagine the cubed root of 17 is, please solve the equation x cubed minus 17 equals 0.
Okay, I gotcha.
You cannot come up with any polynomial equation where pi is the solution or e is.
So are these true statements that you can write x squared equals 2, and that defines what root 2 is, or not defines, but that would correspond to, solving that for x would be root 2.
Right.
It's just, it wouldn't be a rational number that would be the answer. It would be an irrational.
Yep.
But you're saying you can't just write out some formula like that to say, and if you could solve for x, then that would be pi.
Correct. Yeah. No, pi is not the solution of any polynomial equation with rational coefficients.
And people might be confused, like, what are you talking about? I write, 4 pi r squared, but no, there you're putting pi in the equation. We're not saying there can't be an algebraic equation with pi in there as a symbol.
Right.
But we're saying if you wanted to solve for what is pi, you can't do it. Okay.
Exactly. And again, those results that e and pi are transcendental are highly non-trivial. So that's that, and that's why I say once you have accepted the natural numbers as an infinite set, that's what I mean when I say that you've given the game away, because you can very canonically move from the counting numbers to constructing the whole real line with not a lot of effort. So that's sort of the background there. So now why don't we get into let's get into the Riemann rearrangement theorem.
Okay. Let me just to make sure we're finishing.
Yeah.
So this is true? Are these true statements that because I love the building up stuff. So the rationals and the irrationals put together are the real numbers?
Correct.
Is that a true statement? Okay.
Yes.
And the real number are basically anything that could be on what's called the real number line. And that's why. Now can I ask you, because I know you in the email to me, you said you didn't think there was anything, like Steve and I were having fun with I, calling it imaginary.
Right, yeah.
Can we, since we're kind of talking about this, would it make sense to hit that first?
Yeah, sure, we can do that.
And then we can, I don't want to lose the train of thought, even though the rearrangement is like the meat of what we're trying to do here in this episode. Okay, so is there anything, when you said rational, you said that's because they could be expressed as a ratio.
Mm-hmm.
So does it have anything at all to do with, well, this makes sense, whereas the irrationals kind of don't make sense? You know what I mean? Like,
yeah.
Or is that completely like, no, that has nothing to do with that? Because wasn't there a thing, I know you said you don't like the history, but wasn't there something where, like the ancient Greeks, or there was some sect where when they found out about the square root of 2, they wanted to commit suicide or something? Like it really bothered them that it was irrational?
Yeah, so I'm going to engage in rumor and hearsay at this point.
Why not? This is a podcast. This isn't peer reviewed.
Right. Alex Jones is coming over in a minute. So the rumor has it that was the Pythagoreans, that they would get bent out of shape with the irrational numbers. But of course, again, it's really not that hard to generate an irrational number if you just draw a square. These things occur somewhat naturally. That said, this is why I'm saying.
By the way, in case people are saying, well, how wouldn't like a 3, 4, 5 triangle would be fine and be well behaved?
No problem.
You don't have any. They would all be but then if you do, oh wait, but what if it's 1-1? Then what's the hypotenuse of that
what's
one?
the hypotenuse? Yeah, but here's the thing. Like I said, it's rumor and hearsay. I've never looked that story up, so I can't comment on whether or not that's true or.
I mean, I saw it in a book. I didn't see it in a Reddit thread, but just because it's in a book doesn't mean it's true. But
right. Well, that's
where I was coming from, though, Ian. The reason I'm not just merely like, hey, let's take a minute to talk about guys who are really into numbers.
Sure.
What I meant though was, from their point of view, there was a sense in which rational numbers made sense, and irrational numbers that doesn't even make sense.
Yeah.
So I was wondering, was there more to those terms? Because also, I think it makes sense to call the real numbers real and imaginary numbers imaginary. Like, I don't think those are just completely arbitrary labels, even though I know you're going to push back on that in a second.
Well, I guess rational in my mind does derive from the word ratio. And when you complete the metric space, so you've embedded the rational numbers now in a larger set of numbers, and you just say to yourself, well, what's the complement of the set? Okay, well, if this is rational, what's not rational?
Well, how about that? I'll push one more time and then I'll drop it.
Yeah, go for it.
And then we'll go on the. How about though? Because is it true with the rationals? If you express them as a decimal, they repeat. Like there's repeating.
Or they terminate.
Is that true?
They repeat or terminate.
Or they terminate.
Yeah.
Okay, so, and so folks like 1/3 is 0.3333 forever, and there's even ones. Do you know one off the top of your head where there's like a string of digits though that starts repeating?
Well, yeah, like 1/7.
Okay, which is what? I don't know if that is the top of my head.
0.1428, and then 3 more digits.
Okay. That then just keep repeating. Okay.
Opening up my calculator right now. 0.142857. Okay, I guess I lied. It was only 6 digits repeating.
And then it just keeps doing that for, okay. So there's that. Whereas the irrationals, if you start writing it as a decimal expansion, there's not going to be any pattern. It's not like you just do out to the 13th, and then it's going to be those 13 digits again and again and again forever.
Right.
You just got to keep generating new ones. There's partly like with the pi, how people will have, there wouldn't be contests to memorize 1/7 and to see how many digits of 1/7 could you memorize. Whereas
it'd be a very boring contest.
Yes. So a lot of ties.
Yeah. Right.
Or I guess or a lot of just to see who could stay up the longest.
Right.
So okay.
I actually want to make a point about that, though,
Yeah.
because this is important. Well, it's important to me. I don't think it's important to anyone else. But that's one of those facts that you learn in. This is why I'm sort of sympathetic to that episode with Patterson, is because that's one of those facts that you learn in grade school, that rational numbers have repeating decimals or terminating decimals, and then the irrationals are the complement. Their decimals neither repeat nor terminate. You never see a demonstration of that. But in fact, there is, and that result holds no matter what number base you're using. And there is a way to, if you hand me any number, say between 0 and 1, that is rational, there is a way to create those expansions mechanically, so that, and to demonstrate that irrational numbers do not have that. There is a way to do it. All it really requires is a first course in number theory. But of course, most grade school students never make it to a first course in number theory.
Right.
So I wanted to make that point clear to people that you actually do have to put some work into that, but that result does hold.
Well, anyway, though, but so where I'm coming from, though, is just to say, to me, it does seem like I could, for sure, it would help me remember the labels. Like, wait, which one's rational? Which one's is that? There's a pattern to the rational ones. You know what I mean? So you can imagine like like if someone wants to make an argument for the existence of God and say nature is rational, like there's patterns out there, there's laws, the regularity. Whereas if it's just, no, we don't know what's coming next ever, it's irrational. You see what I'm saying? So anyway, okay. But now the one that I'm more confident of is
imaginary.
So you've got the real numbers.
You got the real numbers.
About what that is.
And you're feeling good.
What would it mean to be an unreal number? It would be imaginary. And so you see, like linguistically, they're contrasting. There's numbers that are real, and then there's numbers that are imaginary. And the building block to how do you go from the real to the imaginary is this thing called I, which is defined as the square root of -1.
Yep. So, first of all, just a comment on the nomenclature of mathematics. No one included me in the voting process for that. I would have chosen different ones. But you are correct that when you move from the real line to the complex plane, often, not often, always, you call that additional piece the imaginary unit, the imaginary number. And I think the
Do you know, is that why they called it I? Is it I for imaginary, or do we not know that? Okay.
I always assumed that was true.
Some guy, Igor, was the one who thought of it. Yeah.
No, I believe it was Hamilton, although I'd have to go back and look. Because I definitely know he came with the quaternions, which is an extension of the complex plane. But anyway, the construction of the complex plane from the reals is actually an algebraic one. And it is very similar to how you get the rationals from the integers. And so the way you get the rationals from the integers is we write, when we're doing with our rationals, we write, A over B, right? Like 7 over 3 or something like that. But really, if you wanted to formalize it, you could think of it as an ordered pair of numbers. So 7 over 3 would be the ordered pair 7, 3. Right? Okay. And the extension from the reals to the complex plane is very similar, which is that the complex plane may be thought of as ordered pairs of real numbers. And you extend the arithmetic of the reals to those ordered pairs. And then in particular, and so the real line is contained in the complex plane for the ordered pairs where the first component is some real number and the second component is a 0. And so you can think of that just like with the real plane, right? If you move from the number line to the plane, the x-axis, that's just real numbers with a 0 and the y. That's how it looks in the complex plane as well. And that extension is algebraic because it's saying, okay, fine, we can now consider polynomials with real coefficients, for instance. We want to solve the polynomial x squared plus 1. It's the same thing. You need to extend your numbers in a canonical way. And there's a canonical algebraic construction to do that. And that's how you derive the complex plane. But again, the complex plane is simply ordered pairs of real numbers with your addition and multiplication defined appropriately. And when I say appropriately, I mean in a way so that the complex plane really is an extension of the real line. The fact that they're called imaginary is quite unfortunate, but here we are.
Okay. Well, again, last thing I'll just say.
The reason why they're called imaginary is because with each step, it's becoming these new numbers that we're adding in, right? They become harder and harder to conceptualize.
Right.
And the number of people using natural numbers is quite large. The number of people using imaginary numbers in their day-to-day lives is very small. And so as these constructions grow, the set of people who actually care shrinks.
Sure. So yeah, I mean, I think nobody's denying, not even Steve, that we can define these things and what do you mean by it? It's this rigorous and whatever. Just like the dungeon master running the game could say, well, no, if you're third level paladin, this is true, and blah blah. There could be rules and so forth, but it does not necessarily corresponding to something that's quote real. And so anyway, I get what you mean, but for whatever it's worth, to me, it makes sense for someone to say, yeah, these numbers are imaginary because they're based on this thing called the square root of -1, which, if you think about it, that doesn't really make sense. There's no such number such that, when you square it, the answer is -1. But we'll just call that I. Let's go with this on this. And then it turns out to have application to, electricity and stuff.
I mean, you're right. There is no real number whose square is -1. But it is true that when you have your ordered pairs defined appropriately, there is an ordered pair whose square corresponds to -1.
I got it. Okay. All right. Go ahead. Let's jump into the Riemann rearrangement because I've been stopping you and we got the clock is ticking here. We don't have an infinite amount of time.
Yeah. Okay. So okay. Now we've constructed the whole of the complex plane. Good for us.
We got a lot done.
You're right. All in one evening. Okay, so let's talk about the Riemanns rearrangement theorem. So the first thing I want to say is that when you're doing analysis, when you're doing calculus, a lot of what you're doing in those classes is you are trying to make precise ideas related to infinity. Things that are infinitely large, things that are infinitely small. That's what you're trying to do. And it should be observed that all of these things are done in finite terms. So we might, for the purposes of intuition, write something like, 1 divided by infinity equals 0 or something like that. And that gets your intuition going. You get an idea about what's meant by it. But, if you put that in a proof, your professor slaps your hand. That's a no-no. And so a lot of what you're doing in analysis is you are trying to very precisely define concepts related to infinitely large, infinitely small, that sort of thing. And all of these things are done in finite terms. So for instance, you would say a sequence is unbounded if I hand you any positive number, 5 trillion again, and some positive integer, 300, and you can find some number in the sequence past the 300th term, which exceeds 5 trillion. Okay, so that's what it means to be unbounded. But notice that when I defined unbounded, I did it in purely finite terms. Here, I'm going to hand you two. I'm going to hand you two numbers. You're going to hand me back a different number. It's all done in finite terms. There's no, infinite symbol anywhere in there. Similarly, when we say a sequence converges, so if you have a sequence of points converging to something, well, what do we mean by that? Well, what we mean is that the sequence past a certain point, if you hand me a very small number, if you hand me a very small number, I can find some integer such that all the members of the sequence past that point are within that small number distance of the proposed limit. And so again, this is all done in finite terms. You hand me an error tolerance, I hand you back a positive integer and say, past this point, you're within error tolerance for all members of the sequence. Okay. And so that's what you're trying to do in calculus. That's what you're trying to do in analysis. And one of the things that you have to do is you admittedly have to be very careful with these things. In the sense that, and again, this is where I think Patterson is correct, because in practical terms, we never actually do an infinite number of things, right? All of our intuition is built in the finite. And so a lot of what you're doing then, when you're doing analysis, is saying, how much of my intuition extends to infinite processes and how much of it does not? And so what I thought I would do was take you through a few examples to sort of build this up.
Okay.
So let's share, kind of see what can go wrong.
So for folks who are listening to the audio, Ian is sharing a screen. It's like but it's going to be a PowerPoint.
Yes.
So you may want to, when you get a chance, folks, slip over to the YouTube version, which you can get at the show notes page.
Yep. Okay. And so this first example is sort of a classical one, and it's what happens if you start playing fast and loose with infinity. And so on the left-hand side here, we've got 0. And you say, well, 0, that's no big deal. I can write 0 as this infinite sequence of zeros. Surely 0 is equal to an infinite sum of zeros. And I can take each one of those zeros and I could write it as 1 minus 1. And then I can reassociate. Put a 1 up front. So now I've got 1 plus pairs of -1 plus 1, but all those pairs equal 0. And so that's just 1 plus a bunch of zeros. And of course it equals 1. And I just prove 0 equals 1. And oh my goodness. But of course, what's going on here is that you're being sloppy with your infinite series computations here. Is really what...
Can I stop you, Ian?
Yeah,
so
sure.
I mean, can you keep that big?
Oh, yeah.
You just did something that made it shrink. So I just want to make sure, because it took me a minute or not a minute, but it took me a second to figure out what you just did there. So So I think for people looking at home, so it's 0, and then he's going to clearly that equals. You didn't include this, but you could imagine it being 0 plus 0 plus 0 plus ... forever.
Right.
Clearly 0 equals that.
Yeah.
And then you could for each of those zeros and those sequence, you could, instead of writing 0, you could write in parentheses 1 minus 1, right? Because that's 0. So how could that possibly change it? Right. Correct. And now that you have that with those parentheses, all you're doing, right, Ian, is just moving the parentheses 1 unit to the right.
Yep, you're just reassociating. You're applying the associative property an infinite number of times.
Right, and that for any finite sum, moving the parentheses like that's not going to change the answer, so it shouldn't change it here.
Right.
And yet now, if you look at that expression that's sort of in the in the middle, a little bit to the right, if you're looking at the screen here, it's 1 plus, and then in parentheses -1 plus 1 plus, in parentheses -1 plus 1. So it's now 1 plus a string of things that are 0. And so you just proved apparently that 0 equals 1. So something's screwy.
Yep.
And I guess, Ian, you're going to say this is kind of like the simplistic version of what was making me go, what the heck? They're doing something crazy.
Yeah. Well,
and so
the difference here is that the explanation here is, clearly 1 doesn't equal 0. The explanation here is that you're playing fast and loose with your infinite sums. And if I ask you to actually write down the series that's represented by each one of these things, you wouldn't actually be able to do that. That's the thing, and that's where the fallacy is here. But this is the kind of thing you start toying with when you start getting into calculus and analysis and really trying to. What this demonstrates is you have to be very careful and clear in your reasoning, which again is why all of these concepts are defined in finite terms. Okay.
Well, can you just dwell on that a little? Because I agree with you. This is awesome, and I'm glad you took the time to type this up and everything, because I think this really does get to the heart of it, where I might have, because this, to me, this seems kind of like when you do this, like 1 plus 2 plus 3 equals, what is it, like -1/12 or something? You familiar with that one?
1 plus 2 plus 3 equals -1/12.
Yeah, it was.
I've never seen that one.
The Ramajan guy, or the Indian prodigy.
Yeah.
That the one guy discovered and brought to England or something.
Riemanns.
That was something apparently I think he proved, and it goes around Twitter every once in a while. And there's obviously it's not like they say, well, now what do we mean by this? And they have all kinds of summation symbols and things.
Right.
But the way it is billed is to say, hey, did you know that 1 plus 2 plus 3 equals -1/12?
Right.
And so anyway, that kind of looks like this to me. And yeah, so here you're saying, no, this is wrong. And so can you just one more time just explain why can't I just move the, because I would have thought I'd be allowed to move the parentheses. and I imagine if that never led to a weird result, everyone say, yeah, go ahead.
Yeah.
And it's only because we know it leads to something blowing up in your face. Like, whoa, I guess you can't do that after all.
Well, the real reason is praxeology. Is when you go to the bank and try to convince them that 0 is 1, that it just doesn't fly. But the real reason is I committed the sin right after the first equal sign. See, I got you right there. And the reason why is because that series, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. When you add that up, again, you have to be careful with your reasoning. What does it mean for an infinite sum to converge? It means that the partial sums, which are finite, the partial sums converge to something. Well, the partial sums of that series are 1, 0, 1, 0, 1, 0, 1, 0. They don't converge to anything.
Okay, yeah. All right, let me translate. So, number one, what you're saying is the mistake was not, or the illegitimate move was not shifting the parentheses to the right one number each.
Yeah.
The mistake was in the first move when you said 0 equals, and then a thing, because for any finite truncation of that series, if you just started, if you just look at the first digit, it's 1. Then the second one, it's 0 because it's 1 minus 1. And then the third, it's back up to 1 again because it's 1 minus 1 plus 1.
Yep.
And then the fourth, it's back to 0 again. So every time you add a new term to that, it just goes between 0, 1, 0, 1, 0, 1. Even if you do a trillion of them, and it just keeps bouncing back and forth. It's not that each new term gets smaller and smaller so that the whole thing converges. As opposed to something like 1 over 1 plus 1 over 2 plus 1 over 3, like that. Like, whereas that I realize you can get, Ian, you can go ahead and get into like divergent, convergent series and things, but
Right.
I'm just trying to get people to get their mind going as to what would it mean to say it can go on forever, and it does actually get smaller and smaller.
Right. Yeah, exactly. And that's the thing is that, again, what it means for an infinite sum to converge, it's all defined in terms of finite terms. And what it is the partial sums have to converge to something. The partial sums in this case don't converge to anything. They bounce back and forth. It's a divergent series. And so, so this the point of this example is, it's in some sense, it's in contrast to Riemann's rearrangement theorem, because his theorem is correct. Pardon me. Whereas this is a fallacy. And I'll...
Well, yeah, right. I mean, you just put your finger on it. Like, it's, to me, it sounds like what Riemann's showing is that this, and so I want to say this is nonsense. So I like how you said, well, no, the way we prevent this from happening is to say what you did was illegitimate for these reasons. Okay.
Yep.
And so I would like Riemann's theorem to be wrong.
Well, we'll get there. We'll get there. Okay. So we good on this one?
Yes.
All right. So let's proceed. Okay. So now I want to. So now from now on, we're only going to handle true results here. But I want to continue on this theme of...
I should make that a pledge for this whole show. From now on, the Bob Murphy Show, we're only going to state true things.
Great. But anyway, the point of these next examples is basically to show you, look, you have an intuition for finite matters. Some of that intuition gets ported over, some of it doesn't, and so you got to be careful. And so here's another example of that. So I have here, consider the sequence of functions fn equals I subscript the interval, open interval, n minus 1 to n of t. Okay, so what is that? That's an indicator function. And so here's what it looks like. And so all it's saying is f1 is the indicator function for the interval 0, 1, which means that the function is 0 almost everywhere. It turns on at 0. It's 1 up to 1 and then turns off again. So it's just a signal. And then f2 would be it's off until 1. It turns on at 1, turns off at 2, and so on. f3 turns on at 2, is 1 for a unit, turns off at 3, and so on. And so that's what fn is. It turns on for an interval of length 1 and then turns off.
Okay.
And so you remember that, and so then you can ask yourself, okay, well, consider the sequence of integrals. So what's the integral of this thing? Well, the integral of this thing is just 1, because it takes the value 1 for an interval of length 1, and then it turns off again. So this is length 1. Okay, fine. And then here's f2, and then here's its integral, and then here's f3, and here's its integral, and so on. Okay, well, what just happened here? Well, what happens here is that the conclusion is that each of these integrals is 1, so you have a sequence of 1s. The sequence of 1s clearly converges to 1. But as we saw in the last slide, 1 is not equal to 0, but 0 is the integral of the limit of the functions. Because the limit of the functions, because they turn on only for a unit in an interval of unit length and then turn off, the limit of the functions is just identically 0. And so here you have a case where switching integration and taking a limit, they don't cohere.
Mm-hmm.
And so this is another example where you would like the integral of a limit to be the limit of the integrals, but it's not true. And again, that's because when you start dealing with infinite processes, your intuition doesn't always pour onto it. And so then in analysis, what you would do is you would say, this sucks. Well, what can we do about it? Well, let's come up with conditions under which this is true. Let's come up with conditions and prove theorems and say, all right, well, when is it the case that the limit of integrals is equal to the integral of a limit? And so probably the most celebrated result coming out of that would be the Lebesgue-dominated convergence theorem, which gives a very general condition which says, if your sequence has this property, then you get to do your limit switching. Otherwise, no. You can't do that. All right. We good on this one?
Yep.
Okay. And so now we're going to start really moving toward Riemann's theorem. So consider this function. So this is a function. This is the indicator function on the negative reals times -2 plus 1. And so what does this look like? It looks like this. You've got it's on up until 0. You multiply it by -2 and add 1, so you get -1. And then after 0, the indicator turns off. You just got 1. So it's -1, and then at 0, jumps up to 1, goes onward. Okay, so what does the integral of this function look like? Well, it looks something like this. And this is what you would see in, say, in a Calc 2 book or something like that, where you have a function which takes both negative and positive values. But when you integrate it, because some of them are below the real line and some of them are above the real line, they cancel out.
Mm-hmm.
And so that the whole integral is just 0. Does that make sense?
Yep.
Okay. But this is where we start to have problems that give rise to the Riemann rearrangement theorem. Because what you could do instead is you could take the same function, and instead of taking the integral sort of going to positive and negative infinity at the same rate,
Mm-hmm.
you move at different rates, which I have labeled here as h of x and g of x.
Mm-hmm.
And so if g of x is moving more slowly toward infinity than h of x, then in fact, when you compute these integrals over the finite intervals, you can actually make that integral whatever you want it to be.
Right. Okay.
Does that make sense?
Yep.
And so this is sort of the continuous version of the Riemann rearrangement theorem, which is that if you have these functions which are positive a lot of the time and negative a lot of the time, depending on the rate at which you go to positive or negative infinity, you can make that integral equal whatever you want it to be.
Mm-hmm.
And so this is the difficulty. And of course, that is what gives rise to the Riemann rearrangement.
Now, can I?
Yeah.
Let me try to say something.
Sure.
This probably won't be entirely grammatical, but just I don't want the people at home to be confused. So I believe you're not saying that, for any finite thing that like it's like that right there. What is that? That sums to 1? What you're doing right there?
Well, it sums to A.
Oh, okay. I was thinking that was a unit. Okay, so it's because right there, like the 1 is twice as much. The top thing is going to the positive twice as fast as the bottom thing is going. Is that right?
Well, it's going. It's not that it's going twice as fast. It's just that the top one is. So if you look at the g of x over here, g of x, it just takes its time putting its shoes on, and getting out the door, whereas h of x is already out the door, moving toward positive infinity. And so g of x is 0 for a little while, and then starts moving toward negative infinity. Meanwhile, h of x was already on its way. And so then the result then is that the integral on finite intervals is perfectly balanced, such that on any finite interval, when you're moving toward positive and negative infinity at these rates, your integral is always equal to A.
Oh, okay. So I thought that was that happened to be twice. I just misgauged. It's not that top right one is twice as wide as the bottom left one.
Right.
It's as wide plus A.
Yes.
Mm-hmm. Okay. And so if you kept expanding it, then the bottom one would be even bigger. So they would okay. And so you're saying for stop it at any finite point and then sum up the two things, the net result is going to be A, because by construction, that bottom left thing is going to be a certain width. The top right was going to be that width plus A.
Yep.
Okay. And so now what you're doing though, when you say what's the infinite sum, you're going ahead and letting it go to infinity, but you're saying if for any partial sum, stop it at any point, if that's the way the thing works. So it's not that the bottom thing doesn't eventually go to infinity. It does.
It does.
And the top one goes to infinity to the right.
Yep.
But since the definition of like, what do we mean when we say sum the thing up going to infinity? You say, well, it's the limit. So for any finite stopping point, when you go and check, that top thing is always going to be A bigger. And so no matter how long you let the thing run, the total sum, the partial sums are A. And so to say, what's the limit of this thing as we let it go to infinity, negative infinity on the left thing and the right, it's always A.
Exactly.
And then since A was an arbitrary number, you're saying I could make A anything I want. So I could, okay, I got it.
Right. And so this is, again, that's why I say this is the continuous version of the Riemann rearrangement theorem. So we just took the same function, and depending on the rates at which we went to positive and negative infinity, we were able to manipulate that integral to be whatever we wanted, which is roughly what Riemann's doing with his rearrangement theorem.
Mm-hmm. Okay.
And so, and then again, in both cases, I think you're correct. In both cases, you should stop and go, wait a minute, what? I feel like a sum should always be the same thing. I feel like an integral should always be the same thing. What is this nonsense of, oh, if I vary this rate and vary that rate, I can make it whatever I want it to be? That doesn't seem very well defined.
Mm-hmm.
Okay, and so there is a solution to both of these things, which I will get to in just one moment. But first, the word from our sponsor. No, but first the word about finite sums. So you mentioned this in the Patterson interview, so I wanted to go through it with you. And you said, I could rearrange things any way I want. And you said, I think that's the commutative property. And the answer is, yeah, maybe. But the point that I want to make here is that your ability to rearrange sums of finite numbers and always get the same thing, that's not a property of numbers. That's something that you deduce from numbers. So in the case of n equals 2, it's true, but it's not an axiom. That's my point.
Mm-hmm.
It's a theorem. It's not an axiom.
Okay.
In the case of n equals 2, it's the commutative property. But what about in the case of n equals 3? And so here we've got x plus y plus z. And now the question is that equal to z plus x plus y? And the answer is yes, but you have to do some work. And I just wanted to make a point of this work. So what you have to do is first you have to reassociate. Then you can use the commutative property on z and y. Then you reassociate again.
Mm-hmm.
And then you use the commutative property on z and x.
Mm-hmm.
So the fact that you can do this rearrangement, it's true, but it's a deduction. It's not an axiom. And it should be observed that stop sharing. It should be observed that not only is it not an axiom, it's a deduction, that it's a reasonable question saying, okay, well, we know that it's a theorem in the case of finite numbers. Does it hold true in the case of infinite sets, that we can always do that? And Riemann's rearrangement theorem says, no, you can't.
Okay. Mm-hmm.
And I suppose I also wanted to, this is sort of a tangential point, but I wanted to bring it up, which is that even those properties of commutative and associative, and this goes back to the point I was trying to make at the beginning when I said, we don't make things any more complex than they need to be. The axioms that we choose, obviously for the case of the axioms for the real numbers, basically you can think of them as being derived from ideas of counting, right? That's why we say, okay, things are commutative and you can reassociate. But it should be observed that there are times when associativity doesn't hold. So subtraction is one of them. You get 1 minus 2 minus 3. It does matter the order in which you do those subtractions.
Right.
Another example, and this comes from my friend who's a professor of chemistry and biochemistry, is associativity does not hold in chemistry. So if you combine two chemicals and then a third one, you can sometimes get a different result combining the second and third and then the first. And so the example she gave me is ammonia plus platinum plus chlorine is inactive. But if you take platinum and chlorine and combine it and then add ammonia, all of a sudden you have a chemotherapy medication.
Okay.
Yeah. Okay. And so what's the solution to all this? So Riemann's rearrangement theorem, you can imagine it as basically being a counterexample to the question, can I rearrange things any way I want? The answer is no. But the solution to regain your intuition is basically to say, and this is what mathematicians did. Mathematicians said, wait, this is ridiculous. We want our integrals to be the same number no matter over what region we integrate.
Mm-hmm.
And we want our sums to be rearranged all we want. And so the answer to that is very simple, which is what's known as an absolutely convergent series. So an absolutely convergent series is one where the absolute values of the terms converge. And when you have an absolutely convergent series, then you can rearrange things in any order you want, and you always get the same sum. And the same thing holds for the integral, which is that if you restrict attention to functions whose absolute value is integrable, then it does not matter which regions you consider first when you're integrating. You can integrate over whatever regions you want and take any limit you want, and you always get the same answer. And so that's been the mathematical solution, which is to say, again, you start off by being really clear and you're thinking about how you define concepts related to infinity. You generate examples where you go, well, that's a bunch of hooey. I don't like my intuition being broken.
Mm-hmm.
And then you say to yourself, fine, well, then what are the conditions under which my intuition is retained? And that's absolutely summable series, or what we would say an integrable function. An integrable function is one whose absolute value, that integral exists. And then you move on with your life. And that's how you handle it, is that we just never talk about those series again. We never talk about those functions again because we don't know what to do with them because of these results. And yet, even though we exclude certain series and you're already excluding certain sequences by even asking them to be summable in the first place. So the sequence, an equals n is not summable. So you're already excluding those. You're just excluding a few more. And yet, that which you retain is sufficiently rich to do useful work.
Okay, I think there you just hit the nail on the head, because I could imagine Steve Patterson saying, okay, yeah, so you guys, you're throwing stuff out when it leads to craziness.
Yep.
And I'm just saying, throw infinite sets. That's where the rot comes in. And what do we lose? He's going to say, look, computers can still do their thing. Any operation that humans do in the real world, anything that has actual applications, all take just a finite number of steps.
Yep.
So we don't lose anything. And it's just, your guys, he's not going to stick a gun to your people's heads and say, stop thinking about infinite sets, but he's just saying, you get the point. So what would you say to something like that?
I get the point, but I very much disagree.
Right, obviously, yeah. I'm not trying to I'm not trying to convince you. I'm stating that for you then to give your response. So again, you're agreeing. All we're doing now is disagreeing about what stuff to throw out. Or maybe not throw out's not the right word, but where we need to say,
right,
you got to be real careful from this point forward. And so he's saying, I would draw that line with infinite sets, because up till then, everything makes sense. Everything's intuitive. You start introducing infinite size sets and crazy stuff happens.
Right. Yeah. Okay. Exactly. Okay. So, all right. So that is a fun way to frame the conversation. And the answer to that, I think, is very straightforward, which is that, for one thing, that which I am excluding, and I would say most mathematicians exclude, is far less than he wants to exclude. And so now I simply have to make a case.
And I'm sorry, Ian, but let me state again, when you say you're excluding it, be more precise. Like, what do you mean exactly?
What I mean is I don't think about...
That you're not going to bring it up at a dinner party? That's not what you mean. So what do you mean?
It means I don't think about conditionally convergent sequences. Or
you just did.
Yeah. Yeah, for the purpose of this conversation.
You're a liar.
Yeah, but after this...
Starting now.
Never again. After this, never again. I don't think about them because I don't know what to do with them. That's the thing.
Okay.
Because they break my intuition, I don't know what to do with them, and so I don't consider them when I'm doing mathematical work.
Okay, so in theory, and I know this is going off the rails, but that's fine.
That's fine.
So in principle, if some, I don't know what physicist or who knows what, maybe a biologist or something, maybe if they found a really important use for those things, would you then say, okay, yeah, I was wrong. I shouldn't have, now I do need to start thinking about them.
Well, but again, this goes back to the point that the axioms that mathematicians use are to solve problems. If there was some problem that where we thought it would make sense, where we thought considering conditionally convergent sequences would help solve this problem somehow, then that would open up the field of study.
Yeah. I mean, like for examples, an analogy, when I was totally thought Steve was full of it, I mean, I thought it was cute. I would always talk about and I would say they use it in electromagnetism. Like, so clearly there's we can talk about it formally and say what it is. And it's not just doing like spinning off, fantasy stories about, the Narnia. Like, no, it has practical implications.
Right.
Not that there's anything wrong with thinking about Narnia, but you get what I'm saying. Like, it's not just mere like entertainment for mathematicians that like, what if there was this thing square root of -1? Like, no, it really helps us build circuit boards. And so, okay. So is that kind of where you come down? Like in general, you're just saying for these things?
Well, that's true. Well, that's true of all ideas. That's what I said at the beginning of this, is that we have these ideas, but never mind mathematics, almost all of your ideas are immaterial. But when you have those ideas, those inform your actions, and those actions produce real results in the world. So the question is, does pondering conditionally convergent series, does that inform your actions in some useful fashion in the real world? If it does, let's do it. If it doesn't, well, I'm just not interested. That's all. But that's not a mathematical result. That holds true everywhere. So I mean, that's why, for instance, still a very briefly personal story. Originally, I thought I was going to study algebra in my PhD work, and I got to this course, and the professor said, "We're going to classify all nilpotent such and such and such," and I just said,
he said, "What? We're going to do what?" I didn't even catch.
We're going to classify all nilpotent. I don't quite remember what it is. Modules over the integers, or something. I don't even remember. That. An algebraist listening to this probably wants to punch me in the face right now. But anyway, the point is that we were going to define a certain kind of object, then we were going to classify it, and I had no idea why we were doing this.
Okay.
And I said, you know what? I love you, Professor So-and-so, but this just isn't for me. I couldn't make the connection between what we were going to do with that and life. And so to me, it became the equivalent of Sudoku. Sudoku is something that you do for entertainment. If you're able to complete it, it's done rationally, it's done logically. And yet at the end of it, it was purely for your entertainment. People are like, oh, thank God Bob solved this Sudoku puzzle, because now we can, launch the spaceship or something like that.
But it is true. I want to make sure there are plenty of areas of math where the theorists scoped it all out and came up with all the results, even though they couldn't, quote, apply it to anything. And then down the road, people did find like, oh, actually, these results are over here. It actually is really useful in this.
Right, yeah.
So you're not faulting, you're not saying all mathematicians need to have it. You're just saying it's your cup of tea.
Right.
You have a trouble getting excited about something.
Yeah. Freedom to choose mathematics, a personal statement.
Okay. Okay. Because of the clock here, I think you've done, given enough so people can understand the orthodox understanding of Riemann's rearrangement theorem. I really loved, by the way, again, that first PowerPoint one you did. Like for me, I think that was I know you said so much more, but like that, it clicked with me. I got what you were saying and how, oh yeah, I can see how you got to be careful with these things. We did talk about the academy being corrupt. I'm not expecting you to do anything to get you in trouble or so, but are you, even in mathematics, are you going that far or not?
Well, no, the only, but I know we got the clock, but I just want to make one more statement though.
Sure, go ahead. Yeah.
About throwing out infinite sets versus keeping infinite sets, but pruning some of the things on which we concentrate, which is that the thing that people need to realize is that the field of possibility of computation is infinite. If I hand you a data set, there's an infinite number of calculations you can do with that. So for instance, you could Now, typically what you do is, you get like the 5-number summary, min, max, average, median, that sort of thing, right?
Mm-hmm.
But why instead don't you take the product of all the numbers in there, look at the cosine of it, add 54 and exponentiate it? You could just as easily
Well,
do
if
that.
you're Paul Krugman trying to show that inflation is down under Biden, that's what you do.
Right, exactly. And so the answer is that Steve made this point that the computers are doing the real math, but that's not true. Computers are doing the arithmetic. Mathematics, when you're doing mathematics, you are trying to figure out the computations which are meaningful and the ones which are not. And so due to the clock, I won't get into it, but my claim is that when you retain infinite sets, but sort of pay attention to only certain areas, certain results that come out of that, you are able to do mathematics that programs the computers, or that informs how you program the computers. And you do not get that otherwise. And so probably the easiest example of that would be something like the central limit theorem. It's like, why do you compute the sample mean? Answer, strong level large number says it converges, which is an infinite process, it converges to the mean of the population, and the distribution of it is normal. And of course, the normal distribution makes use of both pi and e. Without these ideas that you get from infinite sets, what is the meaning of the computation? It's mere computation at that point. There's no way to distinguish one computation from another. And that's what mathematics gives you. It gives you the ability to distinguish among computations.
Okay. All right.
Okay.
I mean, I don't think Steve would disagree that mathematics, like the theory of math, is what's guiding to say, why are we adding up these numbers and not these ones? Or why are we not turning on the zeros and ones in this pattern versus that? Like, what does it mean?
Right.
And like, you got to have the antecedent theory. So I think he probably would agree there. He would just truncate, though, what's the acceptable range of the theory that it talks, or the domain of the theory. And you're going to say,
he could try.
There's so many practical things we can't do if you don't let me use infinite sets.
Correct.
Including, like you're saying, what do we even mean by pi and e?
Well, including the most basic results for the sample mean. The sample mean is one of the most basic statistical computations, but you can't say anything about it if you don't allow for infinite sets and their consequences.
Okay.
So no, the only thing I was going to say about the Academy is I'm not saying that the Academy is corrupt. I'm saying what you guys observed.
Well, that's what we were saying. Like, so in terms of the going through, and so yeah. So what's your commentary on that part of our discussion?
Commentary on that's very basic. It is simply that I think what you guys were observing is not a function of the Academy. I think that what you were observing is a function of humanity. Because really what you have is Are you saying that professors are people? I'm saying, in the words of Depeche Mode, that people are people, and that you will find sloth and snobbery wherever you go. Snobbery is just an absence of charity, and sloth is when you haven't done your homework. I, like you, have gone through classes, because you were talking about you were making a point about the class that you took on, I think it was, you were looking at game theory and Nash equilibrium or something like that. You kept asking the professor, what's the meaning of this, right?
Yeah.
And he couldn't tell you. And look, it's not like I haven't had professors who get up there and they're whipping their chalk back and forth. And I go, wait a minute, how'd you make that move? And it's deer in the headlights. I had those professors too. But that's just your run-of-the-mill sloth. Well,
to be fair, the guy that I was asking, he was a deep thinker. It was just he didn't care. Like, it's just not how he was thinking about it. You know what I mean? Like, so It wasn't that he was lazy. It was just to him, like, what do you mean? What does it mean? I'm just telling you that's what.
Right.
Let's come on. So.
Well.
Okay. So go ahead.
Well, no, that was just my point about all that stuff, is that it's incumbent on every person, every student to, and again, if you're going to act on information, you need to verify it. If I go to the bar and I talk to the guy next to me and he says he's a brain surgeon, I'm not going to check and see if he is. I'm just going to assume that what he's saying, that he's telling the truth for the sake of conversation. But if I need brain surgery, you better believe I'm going to check up on his credentials. And similarly for the Academy, is that you're going to have good professors, you're going to have bad professors, you're going to have snobs, you're going to have nice people, you're going to have thorough guys. I worked with some great guys in my graduate training, and I worked with some sloppy people who, when you would ask them a question, especially in undergrad, and they'd go to the back of the book, and you're like, dude, you're not filling me with confidence here. And so I suppose my injunction to people is just to remember that, yeah, professors are people too, and it's incumbent on the student, just like anywhere else, caveat emptor, to vet these people and to, the reason you get an education is because you want to act on that knowledge. So it's incumbent on you to verify that knowledge, trust and verify. That's all. That's all I wanted to say about the academy.
Okay, I think we got about 5 minutes left.
Sure.
I would, of the stuff you sent, we're having to skip some of it.
That's
it's
fine.
porous. You have you sent the real outline, and we're just hitting the rationals.
Sure.
So the part about Steve had suggested that the solution, there's all these like Zeno's paradox, and here I am at the starting line, and the finish line's over there, but before I get to the finish line, I got to get to the halfway point. But before and he's saying, if you just assume space is discrete,
right,
it all goes away. All these problems. So see, like these mathematicians are just loading us up with paradox and nonsense, and everything just makes so much more sense. It's intuitive, and we can solve practical, real-world problems if we just assume finite things, including the idea that space itself is finite.
Sure.
Which, after all, isn't that what quantum mechanics tells us?
Right. Sure. Okay. So I can address that very briefly. And well, for one thing, I'm not going to comment on quantum mechanics because I've never taken a course in it. So
okay,
that's that. But with respect to Zeno's paradox, I don't know why people get so bent out of shape about Zeno's paradox. I'm going to solve it for you very quickly here. So here it is. So suppose it's noon and you're traveling at a constant speed of 60 miles an hour and you have to traverse 120 miles. Okay.
Mm-hmm.
So Zeno would say, well, you're going to do half the distance and half the remaining distance and so on, and thus you never get there. That's his paradox, right? Mm-hmm. It makes undergraduates' heads explode. Well, the solution to that is really simple. My question to Zeno is, well, what happens at 2 o'clock? It's noon, you're going 60 miles an hour, you need to traverse 120 miles. What happens at 2 o'clock? What Zeno fails to take into account is that traveling half the remaining distance takes half of the remaining time. And so traveling half the remaining the distance from the starting point took an hour. Traveling half the remaining distance of that took half an hour. Traveling half the remaining distance of that took 15 minutes, and so on. So all that Zeno is really observing is that you're not going to get there before 2 o'clock. But we already knew that. In the words of George Carlin, all destinations are final. If you haven't gotten to where you're going, you aren't there yet. And the solution to Zeno's paradox is simply to remember that there's a time element to it. And so that each one of his halves, each time he halves the distance, he's also halving the time.
Mm-hmm.
But 2 o'clock comes eventually. The reason why I find it so, I guess we don't need to make a comment about reality. And that was something that I thought was sort of unnecessary on Patterson's part, was that mathematics is just, it's straight deductive philosophy, with quantity as its first abstraction. Steve's trying to solve an intellectual problem by making a statement about reality itself. I'm not making any statements about reality. I'm simply saying that pondering certain ideas allow me to act in a fashion which produces useful results. That's all.
Let me just try once more with the Zeno's thing, just to make sure I'm getting what you're. So the classical statement of the problem is, for me to get from here over there, I first have to cross the halfway point.
Mm-hmm.
But before I can do that, I got to cross the 1/4 point. But before I do that, and so it looks like there's an infinite number of things I need to do.
Yep.
And so how can I do an infinite number of things?
Yep.
So it's a paradox because we know I can walk from here over there.
Yes.
Like we know that it happens. And so the way Steve wants to solve that is to say, at some point, like when you get down to, the smallest discrete unit of space, like it's just you can't refine it. You can't subdivide it further. It's just you're either here or you're there.
Yeah.
And then, so there's a finite number of positions, without taking too strong a stand on, what are the constituents of matter and stuff like that.
Right.
But if space itself is finite, then that's the way he would solve it. And so he'd say at some point you can't subdivide it anymore, and then you're either here or you're there.
Yep.
And, you can talk about, well, how do things move? I don't know, but it's not that there's an infinite number of things you need to do.
Right.
And I've heard other explanations solve it and just say, why can't you do an infinite number of things in a finite time? Who said you can't do that?
Yeah, I'm just saying something much more basic.
So what are you saying?
I'm saying something much more basic than that. All I'm saying is that all Zeno is really observing is that the finite sums of the sequence 1/2 plus 1/4 plus 1/8 are less than 1. And so therefore, you're not going to traverse the whole distance. That's a true statement. But my point is just to take into account the fact that there's a time element. And so, again, the basic sort of algebra problem, right? If it's noon, you're traveling 60 miles an hour, you need to traverse 120 miles. Okay, Zeno says you're gonna do 60 of those, and 30 of those, and 15, and so on. And my point is, well, the first 60 is going to take an hour, the next 30 is going to take half an hour, the next 15 is going to take 15 minutes, the next 7.5 is going to take 7.5 minutes, and so on. But eventually 2 o'clock comes.
Okay, I think I get it. So you're taking what his challenge is to say, you're going to get closer and closer and closer, but you're never going to quite get there.
But you're shrinking your time interval.
Right, but you're so the way okay. Whereas the way I've heard the paradox stated is more like you can't even get started. So it's not that you're going to get arbitrarily close to the end goal, but you keep having further milestones you got to hit. It's more like, how do you even take a step? Because before you take one step, you got to take half a step. You know what I mean? So it's like,
oh yeah, I guess
there's an infinite number of waves hitting you that you can't even. So again, with all this stuff, we know it's not correct, because you can walk. You can get somewhere. Well, but the answer is what's the solution?
But the way you've set it up there, what that means then is that no time is progressing.
Right, yeah.
So it's true. If no time progresses, you haven't taken a step.
Yeah. Okay. I do like that. That might even have some implications with praxeology. I'll have to think about that. I do like that. Yeah, you're right. So what you're kind of saying is, yeah, they're just right. If they slow down the you're like, whoa, right, you're not moving. No, you're not moving if we slow down the passage of time. Exactly right.
If you keep slicing up time finer and finer.
Yeah.
Yeah, I don't know what to tell you. They can't do anything in zero time.
Right. Okay. Well, we are out of time, folks. And so thank you for listening. Right. So thank you so much for your time, Ian. This was fascinating and not the run-of-the-mill podcast episode, I'm sure, by anybody's imagination. And by the way, just I did look it up, and it's the Riemann summation. 1 + 2 + blah, blah, blah equals -1/12. I'll send it to you if you want.
Okay, yeah.
Ian. So obviously, again, they do some tricks, what do we mean? But
sure.
Okay. All right. Well, thank you again, Ian, for your time. Thank you, folks, for tuning in and listening to this unorthodox podcast, but I'm sure we all took away something valuable and interesting. Okay. See you next time, everybody.
You've just experienced another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. For more information and to subscribe to this podcast, visit bobmurphyshow.com.